But before we get into some of those common applications, let's talk about one other way that we could list, or two other ways that we could list the relationships among vertices. So computers need to be able to represent a graph, and they can do it with sets like we've done up here at the top, defining the set of vertices and edges, but there happens to be a more efficient way to do that. And these are a little bit better for computers. For example, we can build what's called an adjacency list. Each vertex in the list is followed by a list of all other vertices it is adjacent to. So we'll just list it in kind of more of a visual form, but we can list the vertex and all of the neighbors of that vertex, or all of the adjacent neighbors of that vertex. So if I list Anne, I see that Anne is adjacent to Bob, Diana, and Elise. So I could list Bob, Diana, Elise. For vertex B, Anne, Diana, and Carl, or Anne, Carl, and Diana, if I want to list them alphabetically, are neighbors. For Carl, Bob, Diana, and Elise are neighbors. For Diana, Anne, Bob, and Carl are neighbors. And for Elisa, we have Anne and Carl as the neighbors. And this is called an adjacency list. If you're wondering if you've ever worked with Python before, one representation of this would be to use what's called a dictionary to record all this information. So you'll often see this as A, like this with a colon, so that's called the key, and the value for that key would be a set of vertices that are adjacent, and we would repeat that for all of the other vertices in this as well. So an adjacency list is something that's usually data structurally a dictionary in something like Python. I think they call them hash maps in Java, but I'm not totally familiar with that, so don't take my word for it. Now, an adjacency matrix is also a way to list relationships. And here's the process. You're going to make a matrix, and you're going to place a 1 in a cell if two vertices are adjacent, place a 0 otherwise, and then we'll answer a question about what other things we can gauge from this. So here's our graph again, and a matrix is going to look like this. So the matrix is just something you might think of as an array in computer programming. And what we do is we just list a row for each of the vertices, and we also list a column for each of the vertices. So you can see that this has 5 rows and 5 edges, therefore it's a 5 by 5 matrix. It'll have 25 entries on the inside. So we're going to place a 1 in the slot if two people are connected. So for example, A and B, Anne and Bob are connected, so we'll list a 1 because there's an edge between them. And also, Bob and Anne, I'll place a 1 here as well because that's the same connection, so there are going to be some redundancies. This would be really handy if you had a directed graph where, let's say Anne shared information with Bob, but Bob did not share information with Anne, and we could have a 1 in one place and a 0 in the other. But we're not dealing with those right now, so here we go. So A to A, well, Anne isn't her own friend, so we list that as a 0. There's no edge connecting Anne back to Anne. And same thing with B to B, with C to C, with D to D, and E to E. So nobody connects to themselves. And then Anne also connects to Diana and Elisa. So Diana and Elisa is a 1, but does not connect to Carl. And notice that this row 0, 1, 0, 1, 1 is the same thing going down for column A, 0, 1, 0, 1, 1, because again, Anne is connected to Diana and Elisa. For Bob, we see Bob is connected to Anne, Carl, and Diana. So Bob is connected to Anne, Carl, and Diana, but not Elisa. And that 1, 0, 1, 1, 0 row will be the same as the 1, 0, 1, 1, 0 column. For Carl, we see that Carl is connected to Bob, Diana, and Elisa. So Carl is connected to Bob, Diana, and Elisa. And same thing for that column for Carl. Diana is connected to Anne, Bob, and Carl. So we already have Anne, Bob, and Carl. Diana is not friends with Elisa, and Diana is not friends with Elisa. So this would be the adjacency matrix. And you can see that this required 25 values to store, right? This requires 25 values that a computer needs to keep track of. This would be handy if you needed to, if you had a very densely populated graph where there were a lot of edges, something close to a complete graph, because you would want to keep track of all those values. But notice that here, this would be convenient whenever you don't have a lot of neighbors. So rather than have to commit to putting 25 values in memory, which could be a lot more, because typically you have on the order of millions, if not billions, of nodes in real-world situations. So if you're going to have a 1 billion by 1 billion matrix, that is going to be a very large matrix. And if there's not very many edges in it, then it might just make sense to list out the vertices that do have neighbors and to really omit the vertices that don't have any neighbors at all. So how do we decide which to... Oh, and then one other valuable thing here is what is the meaning of the sum of a column or row? Well, if I add 0 plus 1 plus 0 plus 1 plus 1, this tells me that Anne has 3 friends. If I add 1 plus 1 plus 1, that gives me 3 friends for Bob, which is true. Or the number of edges, right? Slash edges. Another way to think about this is that the degree of A is 3 because the sum of row A is 3. Now the sum of column A is going to be 3 as well because it's exactly the same as row A. And so the degree of B is 3. Great, so that gives us some ways of talking about things. Which one do we list? Well, usually an adjacency list is more efficient when the adjacent matrix is sparse. That is, when there are many zeros, meaning that there are not many adjacent vertices. So you may encounter this in certain groups or organizations across the world where maybe the leaders are connected, but everybody's connected to a leader, but not all of the participants of that connection are related to one another. Now, an adjacency matrix is beneficial because mathematics can more readily be performed on it, meaning that we can square a matrix or cube a matrix, and without getting into the mathematics of it, if you were to create this matrix in your calculator, this matrix A, and you were just to raise it to the second power, here's what you would come up with. So here is A squared, and we see that it's not just the square of the elements of the A matrix. Matrix multiplication is a little bit odd. I encourage you to look that up if you're interested. But one thing that we should notice is that the diagonals of the A squared matrix, these guys from top, when we say diagonal of a matrix, we mean from top left to bottom right. Those tell me the number of friends that A, B, C, D, and E have. So the diagonals of A squared tell us how many friends each person has. Which is kind of cool. That kind of gives us the sum of the rows as we were summing them up here manually. If you just compute A squared and look at the diagonals, you can see that. And it's totally, and then again, you see the 3, 1, 3, 1, 0 is the first row, 3, 1, 3, 1, 0 is the first column as well, because we're assuming the friendships go both ways. Now, I'll just write this down, and then we can look at it more clearly. But A squared, the off diagonals tell us, A squared tells us how many paths there are between every 2 vertices via a path of length 2. So what we mean is by way of 2 edges. So for instance, even the diagonals, there are 3 paths from A back to A by traveling across 2 edges. And let's see how that would work. So to get from Ann back to Ann, I could go Ann to Bob to Ann. So because I've traveled from Ann to Bob, I've taken this edge right here. But to get from Bob back to Ann, I've taken a second edge, which is the same one, to get back to Ann. Ann to Diana to Ann is a second way. Ann to Elisa to Ann is a third way. And so in essence, even though it's really telling us how many paths there are between every 2 vertices via a path of length 2, it happens to be for the diagonals that's the number of friends each person has. Now, for example, here, Ann and Bob, there's one way to get from Ann to Bob in a path of length 2. So Ann to Bob, well, there's one direct path, but this tells me that there's one way to get from Ann to Bob in 2 edges. So if you go from Ann to Diana and then to Bob, that's a path of length 2, and that's the only path of length 2, exactly length 2, to get from Ann to Bob. Similarly, if you look at this 3 here, that's the number of paths to get from Ann to Carl by taking 2 edges. So Ann to Carl, here would be 1. Ann to Carl would be Ann to Bob to Carl. Or we could go Ann to Diana and then to Carl. Or we could go Ann to Elisa and then to Carl. And so that's what that tells us. Now you guessed it, A cubed is, the diagonals are not going to really tell you anything in this case, nothing of value. But this tells us how many paths there are between every, so A cubed, and I'll just put, same thing, of length 3. So 3 edges. So there are 2 ways to get from Ann to Carl in a path of length 3. Let's see if we could see that. So I could go Ann to Carl, and we're saying there are 3 paths to get there in a length 3. So we could go Ann, Diana, Bob, Carl. There's 1. Or we could go Ann to Bob to Diana to Carl. That's the second one. Pretty cool. So these matrices are useful for that reason. Now, when we draw graphs, one thing we have to realize is that a graph is fully determined by its vertices and how those vertices are connected to other vertices or incident to other vertices. Adjacent, excuse me. So that begs the question of, if you just gave me a set of vertices and edges, would I necessarily draw you the exact same graph like this? Not really. I mean, with this graph right here, as long as A connects to B, A and B don't have to be left and right of each other. I could grab Bob and move Bob way down here, and just imagine that all those connections are staying the same. I'm just moving where the Bob vertex is, and that graph would still be identical even though it appears different. And we call 2 graphs that are identical based on their vertex and edge set as isomorphic. So basically meaning that they're the same, but they're the same change. They're the same morphed graph. Now that seems odd, but let's go ahead and take a look at an example. So if I draw A, vertex B, vertex C, and vertex D over here, and I draw it like this, and maybe I'll put this one here. Let's suppose that what I did is I kept A, B, and C in place, but instead I moved D up here. Well, as long as A and B both connect to D, there's A, B, C, and I've moved D up here, as long as A connects to both D and D connects to B, then I still have this connection from A to C here, and I still have a connection from A to B as well. This graph can be thought of as isomorphic. It's as if we took this and we just sort of, like a rubber band, stretched it out this way and moved it to that point, while preserving all of the links to that vertex. And so these two graphs are considered to be isomorphic because even though they've been morphed, they are the same. They would have the same vertex and edge set.